before we get started. The refuge is open from sunrise to sunset, so you can come and hike here any day of the week if you're looking to get out in nature and see some good spring wildlife, some good signs of spring. The skunk cabbage is coming up in Chocolate Pudding Pond behind the Nature Center, which is a really nice sign of spring, and seeing some good spring birds. Actually, today I saw my first eastern phoebe, which was really nice. So everything's waking up, and it'll be cool to talk about the night sky tonight. So again, this program is being recorded. If you do have any questions, we'll get to them at the end of the program, and you can ask them in the group chat, and we will keep everyone muted. So the Quag Wildlife Refuge, if you're not familiar, is actually located on the South Fork of Long Island in New York State. We are right between West Hampton and Southampton, so we're located in the town of Quag. And we're a small nonprofit nature preserve, and we have 7 miles of hiking trails. We do lots of virtual education, especially now, but also on-site programs as well. So please feel free to check out our website. It's www.quagwildliferefuge.org, and there's lots of good things to see here. So without further ado, I'm going to pass it over to our speaker today, who is Mr. William Taylor from the Hamptons Observatory, to talk to us about the spring equinox and the night sky. So I will pass it over to William, and thank you for joining us, William.
Thank you so much, Kara. It's great to be here again. We did one of these events last spring, and it was last fall, and it was really enjoyable. I'm going to be talking about the spring equinox as is a day, the science behind the seasons. I'm also going to be talking about some cultural festivities that happen around the same time around the world. And then I'm going to be giving you guys a tour of the night sky in springtime. So let's just get started. I'm going to, let me make sure, before I get started, let me remind you too that this event is brought to you by the Quag Wildlife Refuge. We really appreciate all that they do for nature and for the animals around here. I go there a lot just to go hiking and just to see the birds and possums and other creatures that live there. And I'm also coming to you tonight from the Hamptons Observatory, which is a nonprofit in East Hampton that's dedicated to stargazing, astronomy, education, and just about understanding the night sky for the general public. And we have a large telescope that we want to share with the public one day soon when conditions allow it. In the meantime, we do these programs virtually, and looking forward to the day when we can all do this again together. So I'm going to share my PowerPoint I prepared. So let me open this up for you. Okay, here we go. So the spring equinox, that happens this March 20th this year. And it marks the beginning of spring. It's one of 4 astronomical holidays we have throughout the year. The 2 equinoxes in September and March, and the summer solstices and the winter solstice. So technically speaking, it's not totally fair to call it a spring equinox, a summer equinox, because that's unfair to our friends and relatives and such who live south of the equator, where they have everything the reverse. So the most correct way to call this holiday or this day is the March equinox. But for us, I'm going to give it a northern hemisphere bias. That's where I live. That's where also most people in the world live. So it'll be a little bit unfair, but I'll be focusing on the spring equinox for the northern hemisphere mostly. So spring is traditionally considered a joyful time, a hopeful time. And one of the reasons is that for most of human history, people have lived in total dependence on nature for their daily sustenance, for food, for shelter, for energy, for everything. So during the wintertime, life becomes very hard and difficult for people, obviously. We today in our modern world are a little bit more removed from it because we have a lot of modern conveniences that keep us warm in the winter, keep us cold in the summer. But it's worth realizing that we still, even though we don't realize it, we are totally dependent on nature in order for our existence. So it's helpful to go back into the mindset of that most people have lived in history. Here's a painting by Botticelli. It's very beautiful in Florence. Here is a painting from Japan that features the festival of Hanami, when people celebrate the cherry trees that blossom for just a few days in the spring. And here's a picture from Iran. And I'll be talking more about springtime festivals in Iran, which are culturally very significant. This is from the Divan of Hafez, the most famous poet in Iran, sort of the Shakespeare of Iran. And his poems have been translated sometimes into English. Here's a poem by Gertrude Bell about spring. Sorry, a poem translated by Gertrude Bell. Oh, weep no more, for once again, like spring, shall throne her in the meadows green, and o'er her head the minstrel of the night shall fling a canopy of rose leaves, score on score. The secret of the world thou shalt not learn, and yet behind the veil love's fire may burn. Weepest thou? Let hope return, and weep no more. So this spring and last spring was a very difficult spring for most of us in the world, including Iran, including the United States, because that was when the coronavirus pandemic descended on our species. And so we've been living that for a year, and I think many of us are hopeful that things are beginning to turn a corner, that life may soon go back to normal if things go as they hope to go. But every year, spring has been this note of hope for people, and ultimately it's rooted in the source of all the life in our planet, which is of course the sun. One thing about springtime is that we have a lot more solar energy available in our part of the hemisphere. And because of that, we start to see life come back in full force because all of life ultimately depends on plants using the sun's energy to make food for us animals. Um, Even since the beginning of time, people have tracked the sky in relation to the seasons. Um, Seasons, you can track them through other things too. You can watch the migrations of birds, you can watch the gradual growth of plants, and these all happen on a very regular basis. That is tied up with what's going on in the sky, with the movement of constellations, with the movement of the sun, and sometimes the moon as well. So one of the earliest investigations that people have done is to try to understand the movements of these celestial bodies. This is Stonehenge, of course. To quote Nigel from Spinal Tap, no one knows exactly who these people were or what they were doing, but we think that Stonehenge was one theory is that it's an astronomical observatory in addition to a religious site. And that because if you stand in Stonehenge, if you stand in certain locations, there are other parts along the horizon that are marked out that are special because that is where the sun rises at the summer solstice. That's where the sun rises at the winter solstice. That's where the sun rises at the equinoxes. On the equinox, the sun rises directly in the east, but at other times of the year, it rises north or south of that. So it's actually not too hard to tell when you're at an equinox because that is the only time of the year the sun will rise directly east. And during the equinoctial season, during March or September, the sun is moving along the horizon at a pretty quick pace. Whereas a solstice means the sun is standing still. Once the June sun gets here, it stays here for a while, and it's hard to tell when exactly you're at the solstice. Another way to tell whether you're at an equinox or not is to make a sundial. So all you have to do is find something tall, like a mailbox or a chimney or something, and mark where the shadow falls along the ground. You can do that with little stones. If they all line up in a straight line, you're on an equinox. You're either a March equinox or you are in September equinox. At every other date of the year, you'll find that the line that you get is a curve. So I don't want to get entirely into the science of sundial making because it's a lot of fun and I'll talk for hours. But this is an ancient one, and you can see along the sides in Greek are abbreviations for the constellations, Cancer, Leo, Scorpion, that tell you where the sun was at that moment when during that season. Um, so uh, a really bad way to find out when it's an equinox is to try to balance an egg, by the way. I remember being taught this in school that if you can balance an egg on the equinox, which you can, but you can also balance an egg any day of the year. There's really nothing special about that, unfortunately. But why does the sun shadow make a straight line on the equinoxes and not the other days? It involves a bit of geometry, but a nice way to think about it is that you are the center of the universe. Most of us think of ourselves that way. And that if you are the center of the universe, the sun is moving around you in a great circle, very flat circle, on the day of the equinox. March 20th. But in June, if you're doing that, you're still the center of the universe, but now the sun is moving around you in a smaller circle in the northern direction. So the shadows coming from the sun intersect in a cone. And so when a cone intersects a plane, it makes a curve. So it's a short explanation, but this is basically what the sun does throughout the year. It moves in arcs, so parts of circles through the sky, with us roughly at the center. Again, this is what it seems like to us. In this winter, it makes a short circle in the south. In the summer, it makes a much longer circle in the north. Um, and then on the equinoxes, it's centered directly at the east and west points. So the part that is the daylight is exactly as long as the part that's the nighttime. As the sun moves from one of these tracks to the other, which it does by moving through the constellations of the zodiac, at a certain point of the year, in March, it reaches the celestial equator. So the celestial equator is just the Earth's equator, imagined or projected into the depths of space. So we imagine that the sun is usually in the south in the winter, it moves up towards the equator. March 20th, it hits the equator at a certain constellation. Nowadays, that constellation is Pisces, but in ancient times, it was in Aries. So that begins the zodiac count. By the summer, the sun has moved into the constellation of Cancer or Gemini, depending on the century we're in. And then in June, it travels this northerly path. The reason for all this that was worked out in the Renaissance is that the Earth is tilted at a certain angle and it is moving around the sun. And at certain times of the year is presenting different parts of, of the Earth to the sun. So this is kind of unusual. This is an unusual way of moving. Often people think that the Earth is somehow tilting like a wobbly top. And that's why we have the seasons, but it's not true. The real reason we have the seasons is because the Earth is very, very rigid and is always pointing in the same direction. This direction, if you were to follow it out forever and forever into space, would lead you to a star called Polaris, the North Star. And the other direction, it leads you in no particular star, a very dim star called Sigma Octantis, which we can't see, but you can see from the southern hemisphere. So the Earth is a bit like a gyroscope in the way it moves. If you've ever seen a gyroscope, they act very unusually, and they act even more unusually in space. So here's an astronaut on the International Space Station playing with the gyroscope, and it stays rigidly fixed in a certain position, no matter what's going on around it, no matter how much he tries to move it. Of course, he can move it enough to force it to change, but that gyroscope really, really wants to stay pointed in a certain direction, towards a certain star, probably, if we were to watch it all day long. Um, Now, the reason for this is because the gyroscope has what's called angular momentum. Once something is spinning at a certain rate, it wants to stay spinning at that rate. The Earth, being a really, really large gyroscope, is no different. It doesn't want to move. It doesn't want to change from pointing towards Polaris with its North Pole. But you can imagine that if you were walking around the Earth, walking around the sun, it'd be awkward if you're always pointing in the same direction. Say you're always looking at a certain mountain, always looking towards the mountain as you walk around the fire, which is much closer to you. Normally, if I were to walk around the fire, I'd probably want to turn a little bit at each point so that I'm facing forward. That's my preferred way of walking. But if you're always facing in the same direction, at certain times of your path, you would get your right side heated up by the fire. Sometimes you get your back side heated up by the fire, your left side, and then your face would be closer to the fire. So the Earth is in the same position. If we think of the northern hemisphere as the face of the Earth unfairly to the southern hemisphere, um, then as the summertime, we're facing here. We're looking towards the center of fire, which is the sun. Here is a view of the Earth from above, from the North Pole. And it shows one basic reason for why the seasons happen. There's two. I'll talk about the first one because it's easier. This is the view as we move into the winter of the northern hemisphere. And the North Pole is facing away from the sun. The South Pole is getting the sunlight. Now, for a country like Great Britain, it has a very short path through the sunlight part of the Earth and a much longer path through the nighttime part of the Earth. And that's just because of this non-complete perfect overlap between the northern hemisphere and the illuminated hemisphere. Now, as we move to the spring equinox, and we watch this in country, let's take a look at Great or Japan, it moves at exactly 12 hours through the lit part of the hemisphere, and then at 12 hours through the hemisphere of night, and it continues onwards into the summer solstice, where we have much longer days than we have nighttime. Now, what is the reason that the Earth keeps spinning in a certain direction? Why does it always point towards Polaris um, so much farther away, instead of bending maybe in the direction of the sun, maybe wobbling any which way? So there's a really elegant detour I'm going to make into, I find it elegant, into higher physics, and one of the great discoveries of the 20th century, which is called Noether's theorem. So Emmy Noether was one of the great mathematicians of the 20th century. She made huge contributions to fields like algebra geometry, but she was also made a really important contribution to physics. Her birthday was just 3 days after the equinox, so that's why I'm highlighting her here. And Minotaur's theorem is technical. I'm going to give a simplified version of it, which is that in the natural laws of physics, there are certain symmetries. There are things we can change that don't change the equation or the equations, or that don't change the experiments that would result. So an example is rotation. I can rotate my room around. I can rotate my laboratory around. It doesn't change the laws of physics. It doesn't change what I expect to happen when I do my experiments. Well, Amy Noether realized in her theorem that anytime you have a symmetry in the laws of physics, that leads to something else being conserved. So in the case of uh, rotation, that leads to something called angular momentum being conserved. Um, a different kind of symmetry in nature is that I can do my experiment in Oklahoma and then go to New York, and it should be the same. It doesn't matter where I am in the universe when I do my experiment most of the time. And that's because the experiment, there's a symmetry with regard to place. I can move from one place to the other, physics is the same. And that leads to a different kind of conservation called linear momentum, which is just familiar inertia. When you have a really, really fast train moving down a trail track, it's really, really hard to slow it down. If I throw a baseball in outer space, far away from any planet, it's just going to travel forever and forever and never come back to me. And there's a third kind of symmetry in the law of physics, which is that it doesn't matter too much what day of the week I do my experiment on. Tuesday, Wednesday, Thursday makes no difference. And that's because there's a symmetry with regard to time. And that leads to the third conserved quantity, which is energy. So energy is a little bit abstract, but it's one way, an analogy, possible analogy, not my favorite analogy, but you can think about it as a currency, budget, money, because it can be exchanged for all different kinds of phenomena. So energy is just something that lets you overcome a force, lets you do some kind of work. And we need a certain amount of energy as human beings to survive. I need a certain amount of energy to lift things off the floor. One way we measure energy is in joules. So a joule is kind of technical definition, but you can think about it as how much energy you need to pick an apple off the floor and put it on a table. How much energy do you need to pick up 40 apples? You need 40 joules. If you do this every single second, you're using 40 watts. If you have a laptop, like I'm using right now, that runs with about 40 watts of power. So it's doing the same thing as lifting 40 apples off the floor every second. Very impressive. If you're a human being, you're using about 100 watts of power all the time, regardless of what you're doing, just by staying alive, by staying your body temperature, by staying warm. Um, and the actual physical work you do throughout the day, going upstairs, running, jogging, is pretty minimal, maybe 1 watt on average. Unless you're a super athlete and you might be using 10 watts a day or something. Um, now, in short bursts, you can do hundreds of watts, but you can't sustain that all day long. So we as human beings use quite a bit of energy just to survive. The sun gives out an enormous amount of energy. Hard to even quantify this in normal numbers, but you can just trust me, it's a lot. And it goes in all directions through space, isotropically, which means in all directions the same way. A very, very tiny portion of that sun's energy comes back to Earth and lands on our planet. So we scoop up less than a billionth, around, around a billionth of the sun's energy, which is still a lot because it powers everything on this planet. Everything, with a small exception of a few strange animals live underneath the ocean that live off of geothermal energy. We all live on the sun's energy in some way or another. The sun's energy, when it reaches the planet, supplies about 1,360 watts per square meter. So if you imagine you had a really, really good solar panel, perfect, no inefficiencies, it absorbed all the energy it could possibly get. You point it directly at the sun in space, in orbit around the Earth, you could get 1,360 watts, which is a lot to power most of your appliances around the house. But you would probably need a lot more than that to cover all the appliances in your house. Because I'll talk about that in a bit, but we use a lot of energy in the modern world. Over time, this number is called the solar constant. And it's not completely constant. This graph makes it look pretty wiggly over the time as the sun goes through its different cycles that last about 11 years. But it's only fluctuated between 1360 and 1362, so less than 1% over the whole course of history that we've been observing this. So the sun is pretty steady, which is good for us. It's not a variable star like many of the other stars in the universe. Now, when these packets of energy in the form of photons reach the Earth, they are not equally shared across the whole planet. So the energy that hits the Earth's um, equator or tropical regions head on, this gets the full 100% benefit of the sun's energy. But the closer you get to the poles, the more smeared out that energy is over a wider area. So per person or per square mile, you're getting much less energy, maybe half or a third of what you're getting close to the equator. You can do a simple experiment on your own. I just cut a square and a piece of cardboard, reflected it on a piece of paper. There's the same amount of energy going through this left picture as on the right picture. I just changed the angle of the paper. And if you're doing this in person, you can clearly tell that it's smeared out a lot. It's a lot bigger area. It's dimmer. It doesn't show up that well in the photograph. So this is a good experiment to do on your own. It's the easiest kind of experiment. You need to cut some holes in paper. Um, and we are all familiar with this too on Earth because as the sun's angle changes throughout the day, we get different amounts of energy. If the sun was ever directly above our heads, you would get the full blast of solar energy. That only happens if you live in the tropics. For most of us, though, in the morning we don't get very much energy. In the noon we get the most, and then it peters out again in the evening. In the nighttime we get none. Now, if we take the two parts that make up the reasons for the season, so we get different amounts of energy depending on how directly the sun is hitting us. And we also have different lengths of time that we spend in the sunlight based on our latitude. So the further north you go, you spend less and less time in the sunlight as the winter goes by. You combine those two effects and you get different amounts of energy per person per day. So here is someone who lives in the tropics in this blue line. They get about the same amount of energy every single day. It averages around 400 watts. That's quite a lot. Someone who lives in the North Pole only gets solar energy during the summer, quite a bit of it right at the height of summer because the sun's there all day long in the sky, but not at all in the winter. So on average, it's much colder. And so here you can see us, we'd be closer to this 30th, we're at latitude 41 here in New York, but we have these seasons that result from this. So what is all this energy doing and where does it go? So out of all the energy that comes to us, quite a little bit of it is bounced right back into space again. We never get any of it. 163 watts on average is absorbed by the soil, but that doesn't stay there. So one thing to realize is that everything radiates, not just the sun. You and I are radiating. Anything that has any temperature at all is radiating at some frequency. And warm bodies like ourselves are radiating infrared. So the Earth is also radiating infrared. So if you're standing out there at nighttime, you can imagine the entire ground around you just shooting off energy into space where it disappears. Um, Out of the energy that comes to us every day from the sun, 99.999 or whatever, not that much, but the overwhelming majority of it is blasted into space again through infrared radiation. So there's a balance. If we ever were to absorb more sunlight, which we are over time, the Earth would get a little bit warmer, and then it would also start radiating more energy away once it reaches a certain equilibrium. But the equilibrium can change. And so one factor here I want you guys to all be aware of course, and I'm sure most of us are, is greenhouse gases. Because once light gets, or in the form of infrared, gets radiated away from the surface, some of it goes into space, but a lot of it hits the greenhouse gases, which are water, vapor, carbon dioxide, and methane. And those radiations come back to us eventually. They're stored in those molecules as a form of molecular energy for a little bit, and then they come back to the ground again. So these greenhouse gases work as a blanket for a planet. And on the whole, they make our planet much warmer than they would be if we didn't have them at all. And an example would be Mars, for instance, has a much thinner atmosphere than ours. It's farther away from the sun, but all things being equal, it should be a little bit warmer than it is if it had a thicker atmosphere. Because it has no atmosphere to speak of, it's very, very cold there. Venus has the opposite problem. Too many greenhouse gases, and it's melting point of lead there. Yeah, we would like to capture more of the sun's energy to power ourselves, but it's difficult. And So far, we've been doing a bad job of it. Here you can see how much energy the human race uses on from year to year. It just is skyrocketing from year to year. Solar makes up a tiny, tiny little yellow pixel. I'm not even sure you can see it at the top here. It is growing, I'm sure. It has a long way to go. Other kinds of renewables that are ultimately just a form of solar energy include wind, which is just caused by solar heat, hydropower, which is also caused by the sun raising water and dropping it down again. Um, Nuclear energy is the only one that's really not ultimately solar energy because gas, oil, and coal are just forms of solar energy that were stored up in the earth over millions and millions and millions of years. So the human being in the 20th century has had the great idea of taking these things that were locked up for billions, millions of years and just releasing them all again. Well, what's happened, of course, is that that extra greenhouse gas in the atmosphere has made our temperatures rise. And here you can see it directly from measurements made around the world through thermometers since the end of the 19th century. The average temperature of the world has risen about a degree or more since then. But it's even more dramatic if we try to reconstruct temperatures of the past before the industrial era, going back to Roman times here, through different means, through looking at um, ice cores, through looking at tree rings and trying to determine what the temperature was at different times in history. It's really skyrocketed in the past century. This is something alarming to think about. If we wanted to move to a new society that used only solar energy, it's still really difficult because we use so much energy. The average American, just to give you an example, uses well over 1,000 watts a day throughout the whole day, averaged out. And that's a bit like having a team of 100 servants doing things for you all day long, working like crazy, working at their maximum physical strength for you all day long to heat up your bathtub, to make your home warm, and to drive you to work, and to do all these things. So it's really nothing like any human civilization has has had the luxury of, but it's also not sustainable because it's changing our environment. And even if we were to convert to solar energy, we need the area of basically New Mexico converted into solar panels to get that much energy. So I'm not sure when that might happen, if that would happen. Um, and so we have to really think is like the way we live now is sustainable. If not, we're going to need some kind of major technological breakthrough, like nuclear fusion, which is always promised to happen 30 years from now. But we'll see. Um, it reminds us, though, that it reminds me personally that um, we are dependent on nature, whether we realize it or not. So it's good to kind of go back into a few traditions that were rooted in nature. And we still have these today in our world. We have cultures around the world that celebrate different holidays at the spring. Um, and in the United States, two holidays that are probably the most familiar to people would be Passover and Easter, are usually celebrated around the spring equinox, but they're not directly about the spring equinox. They just um, are aligned with seasons. But Easter, for example, is supposed to take place on the first Sunday after the first full moon after the spring equinox. And actually, to compute this date is a real challenge. And here you see a medieval manuscript about the and mnemonics, I guess, that went into figuring out when Easter might be in any given year. It's complicated because the rhythm of the Earth's rotation and the moon's rotation around the Earth and the Earth's rotation around the sun are three different numbers that don't really make great ratios that are simple. So we have to come up with complicated rules. But one holiday that is celebrated by millions of people that falls exactly on the equinox every year and is about the equinox is called Nowruz. This is a holiday which is celebrated in Iran. It's also celebrated in Afghanistan, Tajikistan, many Central Asian countries, and it's celebrated throughout the world wherever there's a diaspora of people from those origins. This is a girl from Kurdistan celebrating the beginning of Nowruz. And it's a very ancient holiday. So it goes back well over 3,000 years. And in its origin, it's related to the Zoroastrian religion, which was the official religion of the Achaemenid Persian Empire. So here we see some courtiers, I think, from Armenia. This is in a palace called Persepolis in Iran, which was built by King Cyrus. So 2,500 years ago. And in those days, Zoroaster, who we don't know exactly when he lived, but he preached a religion in which Ahura Mazda which means supreme wisdom was the supreme God. That there were two forces in the universe that were constantly at war with each other, which are called Asha, which means truth, Bruj, which means the lie, or darkness. So humans have free will about which side they're going to take. Zoroastrianism proclaims that Ahura Mazda, being the supreme God, ultimately good will prevail, but this world is sort of a battlefield of these forces. One way to think about Nowruz, and it's particular in this religion, is that it's the reemergence of light, reemergence of the forces of truth, in a way, every year. Here is a Zoroastrian priest in the Middle Ages. So for Zoroastrians, fire is a very important symbol of their religion. In some ways, it symbolizes the wisdom of Ahura Mazda, the light of Ahura Mazda. But to this day in Iran, even though the majority of the population is no longer Zoroastrian, people still celebrate Nowruz with complete fervor. So a few days before Nowruz, there's a holiday called Shohor Shanbeh Suri, which means, I think it means the Wednesday of light, if I'm not mistaken, or the Wednesday fire. Usually people make a bonfire and gather around it, but you can also jump over the bonfire, which a lot of people do. It's adventurous, a little risky. But people do it because by jumping over the fire, you're purifying yourself, you are getting rid of all the bad energy of last year, and celebrating the new year, which starts on Nowruz at the exact moment of equinox. Here, people buy greenery for the Nowruz to celebrate this new holiday. People like to make something called the hafzin, which is an array of different items that begin with the letter S in Persian. So Sib is an apple, Sabzeh is greenery. And then the exact moment of Nowruz is determined by astronomy. Our Gregorian calendar, which most countries in the world now use, uses a rule system that keeps us pretty close to the equinox at the same date. Every 4 years, we need to do a leap year, and then there's a more complicated rule to keep us on track there. The Iranian calendar, which is different, uses just observations about when the equinox has happened to keep them always on track. So one of the few countries in the world to not use the Gregorian calendars. That makes another interesting aspect of this religion, not religion, or cultural tradition. So here are people celebrating Nowruz on March 20th, or whenever the spring equinox falls that year, always on the first day of the Persian year. So the founder of Zoroastrianism was a prophet named Zoroaster in Greek, but Zarathustra sometimes, a Vestan language. And he was an influence too on the Greek world, on the West, because one of his flaws, his religion was a very philosophical one and was very rooted in ethics. His ethical system was called Mazda Yasna, which means love of wisdom. Well, according to Pliny and other Roman writers, people of the Zoroastrian faith came to ancient Greece and influenced the first philosophers in Greece, like Pythagoras, who called themselves philosophers, which means lovers of wisdom. It's exactly the same word, just in Greek instead of Persian. And this painting, this is the famous School of Athens by Raphael. You can see Zoroaster here holding up the celestial globe and in a conversation with Ptolemy, the writer who wrote about geography. So the two globes of the earth and the sky are deeply entwined with each other. So I'm going to end this part, and I'm going to give you guys a little guide to the night sky that you can see tonight. And that involves a little planetarium show, and also use a bit of Greek mythology. So let me start sharing that screen. Okay, so if we were to go out tonight, this is what we would see right now. If it's clear where you are, if you happen to live in the same part of the world as I live in, Long Island, New York, and we have people here from Turkey, from Australia, from all over places. So this is, again, a local view of what's going on. But this is what the sky looks like in late March. So there's a few constellations that are really distinctively spring constellations. And one of them is Leo here. Leo is part of Greek mythology. All these constellations have a Greek mythological story attached to them. And a lot of them have to do with Hercules. So Hercules was the great strong man who he fought a lifelong of challenges and struggles. One of his struggles was to do what were called the 12 labors. But 12 labors that King Eurystheus gave him. The first one was to conquer the Nemean lion, who was a ferocious lion terrorizing a town called Nemea. None of the arrows or weapons at Hercules' disposal would really work. So he had to take on this lion directly with his bare hands. So you can imagine the strength of this man. The next monster he had to deal with was Hydra, who, as you remember, had multiple heads, multiple necks, uh, shooting fire everywhere, a very dangerous opponent. Hercules needs to team up with his nephew, Iolaus. They need to use fire and poison in order to defeat this beast. So these two monsters, you can call them, are part of the night sky and very close to each other. Here is Leo, looking very much like a lion, one of the nicest constellations to look for because it looks very much as advertised. If we take away these constellation lines, you can still see the outline of what's called the sickle of Leo. And then there's a triangle that makes up his tail. Regulus is the brightest star in this constellation, easy to see. I remember seeing it on a very special day in 2017 when there was a total solar eclipse. The sun was very, very close to Regulus. And so at the moment the sun disappeared underneath the moon's shadow, Regulus popped out right next to it. Surprising. And it gives you a sense of the scale of the universe. Our sun, very far away from a human point of view, 150 million kilometers, but Regulus is millions of times farther away than that. There they were right next to each other in the sky. This is Vesta, which is one of the brightest asteroids. If you have a pair of binoculars, you can see it. And I'm going to focus just on things that you can see with binoculars. Because not everyone has access to a telescope, if you have a pair of binoculars, if you don't have a pair of binoculars, it's probably the best investment you can make if you just want to learn about stargazing. You're just starting off, because a telescope can be a really amazing tool. It can also be expensive and difficult to figure out at first. So when we're looking towards the west, right after sunset, you want to take a look at Orion first, because Orion is going to disappear very soon as we move into summer. It's a winter constellation. So this is the very last of it. If you have a pair of binoculars, taking a look at this part of the sky, the belt of Orion, Alnitak, Alnilam, and Mintaka, and the sword of Orion is probably the most beautiful part of the sky for a binocular user, because you can see the amazing Orion Nebula. Even with a small pair of binoculars, you can see it very distinctly, and it's very colorful. As we look to the right of Orion, you can see Mars, the Pleiades, and what's called the Hyades in the constellation Taurus. This is a fun place to watch too, because Mars is the only planet in the night sky. Mars is very far away. It's not rewarding as a telescopic object because it's so far away. But we can see it moving clearly through this really rich part of the sky, and so that's enjoyable. If we look to the left of Orion, there is the really bright constellation really bright star, Sirius, the brightest star in the sky, and the constellation of Canis Major. Here you can see his head, here is his tail. Sirius makes a kind of jewel on his necklace. So Sirius is a really interesting star. It's one of the closest to the Earth. If you do have a telescope, you can look at Sirius, and it will be a little bit of work and a lot of practice, but Sirius has a companion to it, which is an unusual type of star called the white dwarf, which is as bright as it's as white hot as the sun, but it's only the size of the Earth because it's the shrunken dead remnant of a star that once existed. And you can see it right next to Sirius. For a very good telescope, and you're very patient. It's drowned out in the light of Sirius. If we have trouble finding Leo, an easy way to find Leo is by looking for the Big Dipper. The Big Dipper, most people know this one. And right in springtime is the best time to look at it. It's right overhead most of the time. If we follow the bucket part of the dipper downwards, Leo. These two carnivores, the great bear and the great lion, are always walking in tandem with each other. Now, to see a bear here is a challenge, of course, because unlike most bears on Earth, this bear has a long tail, has very long legs. I like to think about it as some kind of other animal and smaller and cuter. For instance, a red panda looks a bit like this. A raccoon looks a bit like this. So you can use your imagination. No one knows exactly where these names come from. But the name Leo is a really old one because when we look at some of the earliest cuneiform tablets of astronomy that come down from Babylon. They made lists of constellations in the night sky, and one of them from Sumerian times mentions Leo, or a lion constellation, as being the same as ours. It's pretty cool. To the right of lion, to the right of the lion, to the left of the lion, there are two star clusters you can look for. So there's one star cluster on the left that's a little bit easier to see. It's a constellation called Coma Berenices. This means the hair of Berenices. An interesting constellation because it's named after a real person, a historical person who was the queen of Egypt. Um, and one of the legends is that she cut off her hair as a sacrifice. And it made its appearance in heaven shortly thereafter. To the right of Leo, you can see Cancer, the crab, a very dim constellation. And even in ancient times, it was considered very hard to make this out at all. If you're lucky, you can see a crab here, but most people might just see the letter Y. But if you zoom in on it, there's a really beautiful, beautiful thing to look at through a pair of binoculars. It's called the beehive. It's a really rich cluster called an open cluster, um, which typically has hundreds of stars in close proximity to each other. Our sun is not in an open cluster. We're kind of off on our own. But if we were in the middle of one of these open clusters, the night sky would be really different. It would just be bright, bright, bright stars in every possible direction. So we can see a few of those, like the Pleiades, in the winter part of the sky. And here are the Pleiades. We can see the beehive in the spring. To the right of the beehive, you'll see the Gemini constellation. I think this is a cute one because it looks, to me, as advertised, it looks like a pair of twins holding hands. If you have a pair of binoculars, take a look at the foot of Castor, the one on the right. So in the foot of Castor, there's a constellation. That's a constellation, another open cluster you can check out right here. A really pretty one. And zooming out a bit, it's called the shoe buckle cluster. I think it has a more official name, M35. I want to talk a little bit about the Great Bear again, because we should take advantage of the Great Bear being right on the top of the sky. The Great Bear is always there somewhere in the sky, but not usually so well situated. So if we take a look at the head and the neck of the Great Bear, moving right from the bowl of the Big Dipper, you can see a pair of galaxies. This is really cool because these galaxies, most galaxies are really, really hard to see without a telescope. These ones you can see with just a pair of binoculars, and you'll see them as fuzzy spots in the night sky. One is called Bode's galaxy, and the other is called the Cigar galaxy. Bode's galaxy is a classic spiral galaxy, like really beautiful, symmetrical. Nearby is the Cigar galaxy, and it's really unusual. You can see that something violet has happened here in the past. Maybe a collision with another galaxy. A few years ago, I saw a supernova in this galaxy. It was pretty cool to watch. So far away, that was 11 million light years away to these galaxies. So think about it, on Earth, human beings hadn't even evolved yet, just like ancestors around. I'll finish with one more object you can look for that I find kind of easy to find. If you have any questions about any others that you wanted to find, I'll help find them. But if you take a look at the bright star Arcturus, which you can easily see rising after sunset, and will get higher and higher in the sky as the night goes on, you can see another star underneath the handle of Big Dipper that's called Cor Caroli, the heart of Charles. It was also strange. Who was Charles? Well, it's King Charles of England, who was martyred. He was murdered during the English Civil War. And so astronomers who were sympathetic to him named the star after him. So it's another star named after a fairly recent historical person. But halfway between Arcturus and Cor Caroli, you can see a globular cluster called M3. So if you just point your binoculars right halfway between them, you'll see it. It's a fuzzy spot. You might not recognize it as this at first. You'll probably see it next to this other star called but you can tell the difference between them because the star is very sharp and distinct, whereas the cluster is very fuzzy. If you have a telescope, you can zoom in on it, and you'll behold hundreds of thousands of stars in the same moment. These kinds of clusters are some of the oldest things in the universe because they formed just a few billion years after the Big Bang, as opposed to us who formed 30 years or so after the Big Bang. Um, and they've been around since the galaxy was formed. These stars are very, very old. There's not much star formation going on inside these clusters. They kind of orbit the galaxy that we live in. And I find them all inspiring to look at just because you can really see at a glance sometimes a million stars buzzing around each other. And it's mind-boggling to think of what it would be sitting there in the middle of all that. Well, our own part of the Milky Way is beautiful enough to look at, so I encourage everyone to do so in March. One of my favorite things about springtime is that it is warm enough to go outside, but it is not so warm that we have to worry about bugs and mosquitoes and such. So it's the best time of year for astronomy, if you ask me. So I'm going to pause it there, and I'm going to be happily taking any questions from anyone. I know Kara said she would help with that, so.
Yeah, thank you so much. That was a great presentation. And I know a lot of people said that in the chat already. But we did have a few really great questions. I'll just go from the ones that came in first. There were two questions about the Milky Way. One was on April 11th, what is the time of day or night to best see the heart of the Milky Way?
Okay, that's a great question. So the Milky Way is this band of stars. You can see it. Let me make sure I use the on my screen share. Let me share that screen again. Okay, so if you want to see the Milky Way right now, before you go to bed, you can look to the shoulder of Orion. There's a star called Betelgeuse. It was very interesting because last year it faded almost from view. It faded significantly compared to what it normally is. Now it's back to normal again. If you follow Sirius to Betelgeuse and follow along, you'll see a faint trail of light that's called the Milky Way. This is the winter part of the Milky Way, but it's not the heart of the Milky Way. The heart of the Milky Way we usually see in the summertime. So if we're looking on April 1st, let's change the date. You said April 11th, right? Is that it?
That's what exactly, yeah.
Okay, so I'll go to April 11th, and then we'll go through the hours and see when we can see the Milky Way the best. So if we go, I think we have to stay up pretty late. If we stay up to 2 in the morning, or almost 3 in the morning here, you can start to see the center of the Milky Way. That's in the constellation Sagittarius. So Sagittarius is this little tea kettle-like constellation down here. Maybe I can add the names. So Sagittarius is right here. Early morning hours would be the best because the middle of the Milky Way is really a summertime site. But if you're in the springtime and you want to see summer stars, just wait till the early morning because you get a preview of the next season early in the morning. Same thing if you're in the summer, you want to see the fall stars, wait until early in the morning, you'll see the fall star. So the center of the Milky Way is right here. And it's a really, really interesting part of the sky to look at because it looks like a big bulge in the Milky Way. I love it because you really realize that you're in a galaxy when you're looking at this part of the sky because you see the center of the whole Milky Way. It's a really rich place also to explore with binoculars. You'll see lots of nebulas and star clusters. If you have a telescope, you'll see this.
Awesome. And the other question on the Milky Way was, can you explain the perceived movement of the Milky Way?
So there's two questions. I guess I would want to know the perceived movement in two senses because there is the perceived movement through the night sky, which is just because of Earth's rotation. So if let's say, you can see the Milky Way seeming to rise and move through the night sky, right? That's just because all the stars are moving in the night sky. The Milky Way is a band that is kind of like a girdle going around the entire sky, 360 degrees. So we seem to move it. Well, and if the actual movement itself, of the real movement of the Milky Way is very hard for us to perceive because it's very slow in comparison to the human lifetime. So the sun is going around the Milky Way in an orbit, just like Earth is going around the sun. But the Earth goes around the sun in 1 year, but the sun goes around the Milky Way in about 200 million years. So it's really, really hard for us to really see much movement in our lifetimes. If you sometimes you can see a few stars move a little bit in your lifetime if they're pretty close, but the actual movement of the Milky Way is hard to see. However, it's a very dynamic thing. It's just so big that it takes a long time for anything to happen. So if we could live millions of years and watch the whole thing unfold out in a time lapse, it would be like watching water go down a drain. It's spiraling around like a hurricane. It's pretty amazing. Yeah.
Awesome. And then we have a question
Mhm.
from Roger. If the spring equinox is the first day of spring and the summer solstice is the first day of summer, when is Midsummer's Day?
Okay. I think Midsummer's Day, if I'm not mistaken, this is more of a folklore question than an astronomy question, but I think Midsummer's Day is in Sweden, for instance. There's a holiday called Midsummer. I think it's on the summer solstice itself. And that raises actually a pretty interesting thing. So when I say that the spring equinox is the beginning of spring, some of you might notice it's still pretty cold out. It's it's not really springtime weather yet. That's because there's a bit of a lag between when astronomically it's spring and when climate-wise, weather-wise, it really becomes a lot warmer. And so the warmest day, the hottest day of summer isn't necessarily the solstice in June. It's usually in the middle of July or August, right?
Mhm.
Other cultures around the world celebrate the holidays a little bit differently. So in China, they also break up the year into four parts, but their winter. So for instance, for them, spring actually starts sort of in February and ends in February, I think. So instead of it's kind of at the cross quarter points they're called between the spring equinox and the summer solstice. So summer solstice is called Midsummer's Day, I think in England and Sweden and other places. Um, Shakespeare's play, Midsummer's Night's Dream, I believe takes place on June 20th, around then. Even though, from our point of view, it's kind of strange to call that midsummer. We think of summer as going from July to August, and midsummer would be like late July or something like that. But in a way, it's more astronomically accurate than weather accurate. So it's really the middle of that whole season when the sun is above the equator, or goes below the equator. And if you want to say one more technical thing, that's because in a lot of older languages, and to this day in Icelandic, I think, there's only two seasons. There's summer and winter. And summer starts on the spring equinox, lasts until the fall equinox, then it's winter for 6 months, and then it's summer for 6 months. And so that uses a simpler tradition where um, whenever the sun is in the northern part of the sky, it's summer. Whenever it's in the southern part of the sky, it's winter. So that would make June 20th the middle of the summer.
Great. Oh, there might be one more question coming in,
Okay.
but thank you so much. That was an amazing presentation, and I know a lot of people also appreciated it in the chat too. So
Okay, thanks.
thank you for that.
Mhm.
Let's see. Oh, we do have a question. Let me
Okay.
see if I can unmute. I'm gonna allow you to unmute or ask you. Let's see if that worked.
Hello.
Hello.
Hi, William. That was fascinating. You're a very clever creature, and thank you so much. That's it.
Wonderful
Excellent.
question. Thank you.
That wasn't a question. You know how smart you are, stupid.
Okay, stop now. This is my sister, everyone who doesn't know.
Oh, that's funny. Oh, we do have one more question. Where do you find the best telescope viewing is on
Mhm,
Long Island?
mhm.
And also they find that Camp Hero is good, but what are your thoughts?
Yeah, Camp Hero is a great spot. Camp Hero is as far as you can get east, away from everything
Right.
else. That's a really cool spot to go stargazing. I would go there more often if it was a little closer to my house because it's about a half hour from where I live. But it's a beautiful spot. It's right there on the ocean. I'm thinking about going to Camp Hero for a very specific and strange reason. And that's because it's one of the few places I can think of where you can look directly over the ocean from a high spot and see as far as you can to the south. There are certain things that in the springtime, there's one star cluster in particular called the Mega Centauri, which is the brightest star cluster in the whole sky. So far south that it's hard for us to see here in the northern hemisphere, but in April, it comes just above the horizon for a little bit. So I think the only place you could really ever see it from would be Camp Hero. And Camp Hero is just as if for folks who aren't around here, it's near Montauk Point. It's an old army base. It's very dark and desolate. So it's a good spot to go. Other places I tend to go. I can't do stargazing in front of my house. There's too many trees. I tend to go to the beach and anywhere. So I tend to go along the bay beaches. In the summertime, it would be nice to go to the ocean beaches. It gets very muggy down there
Mhm.
because there's a lot of just moisture in the air. So your telescope tends to get muggy pretty fast.
Right. And also, we have another question from Karina.
Mhm,
What's the best spot here to stargaze
mhm.
Lyrid meteor shower?
That's a great question. I actually forgot to mention Lyrids. They're really cool. They're a really nice star meteor shower that happens in April, late April, I think April 20th, but don't quote me on that. It is it's a meteor shower that I witnessed last year from near Camp Hero. Actually, I went out to Camp Hero to watch it, and I can't think of a better spot because wherever you get to be as dark as possible is where you'll see the best time in a meteor shower. One thing about say about stargazing in general is you need as much dark sky as possible. So if you can get as far away from town lights, city lights, that really changes the picture. And also let your eyes adapt to dark. A lot of people are a little disappointed when they go out at first, because you can't see really most stars until your eyes have been adapted for maybe 20 minutes. Um, so if you let yourself get adapted to the darkness, if you feel comfortable with that, you'll see a lot more meteors. And so that meteor shower would be best in after midnight, late midnight, but worth it if you're interested.
Yeah, definitely. Well, thank you so much. That was a great program. And I know I'm really excited for spring, but this is even more, I think, to be excited about when you can enjoy it during the daytime, but also at nighttime
Mhm.
and do that. Well, so thank you.
Thank you so
Yeah,
much.
and thank you all for tuning in tonight. We really appreciate you coming to the program. And if you have any questions at all, please feel free to ask me about the Quag Wildlife Refuge, and I'm sure William as well about the Hamptons Observatory. But thank you all for joining us, and hopefully hope you have a great night. Thank you.